This podcast is brought to you by the School of Advanced Study, University of London.
And thanks to Mattia and Colin Blakemore for inviting me to the Human Mind Project. I'll say a little bit about the Human Brain Project later on. And thanks to all of you for coming out on such a lovely evening when I'm sure you're tempted to go sit outside and have a glass of wine. I certainly am. So let me begin this talk, which is called To Read the Mind in the Human Brain, with a word of warning. Like many people, I've been fascinated by the rise of a popular discussion about the brain and the enormous outpouring of research papers on different aspects of neuroscience and the growing belief that this work on the brain has implications for the world in which we live and for human conduct and for understanding human mental life. Now, a lot of that discussion about these developments has taken the form either of praise or of blame. Lots of people are tremendously enthusiastic about these developments, and lots of people are very critical about these developments. As Mattia said in his introduction, my approach is slightly different. I'm interested in what is coming into being, if new ways of thinking about human beings are coming into being, and if they are coming into being, what are their consequences and where? I'm less interested, at least in this part of my work, with the project of evaluation. And a second word of warning, because I'm going to tread rather heavily on some contested philosophical ground, I should make it clear that this is not a philosophical talk. It is, to quote Michel Foucault, a historical investigation into the events that have led us to constitute ourselves and to recognize ourselves as certain kinds of subjects, and the implications of that. So how did I get into doing the bit of work that I'm going to present to you today? Well, a year or so ago, some colleagues of mine in Australia were putting together a special issue of a journal called Body and Society, on surveillance of the body, looking at the emergence of new technologies of surveillance of the body. And they knew that I'd written this book that Mattia was kind enough to refer to, Neuro, and they said, well, why don't you do a little afterword to our papers on surveillance and the body, on surveillance and the brain and the mind? And I sort of said rather rashly, yes, okay, I will. Okay, I will. And what I'm going to present to you today is kind of where I got to in that exploration and the sorts of things it left me wondering. I'm hoping in the discussion afterwards that you will challenge and help me think about whether I've got this whole thing completely wrong. So just a few words to preface the talk about where we've got to now. In 1950, Charles Sherrington, a very eminent neuroscientist, was introducing a series that they had on BBC Radio on the third programme. And he's introduced that series, which had lots of eminent philosophers and people doing brain research, by referring back to something that he'd said in 1900, 50 years ago. And in 1900, Sherrington had said, we have to regard the relation of the mind to the brain as still not merely unsolved, but devoid of a basis for its very beginning. And as he introduced this series on the radio in 1950, he said this: Aristotle, 2,000 years ago, was asking how the mind is attached to the body. We're asking that question still. Now, fast forward 50 years to another eminent neuroscientist, Vernon Mountcastle, writing actually in a cultural journal called Daedalus, just at the end of the 20th century. And this is what he says: the half-century's accumulation of knowledge of brain function has brought us face to face with the question of what it means to be human. We make no pretension that solutions are at hand, but assert that what makes man human is his brain. Things mental, indeed minds, are emergent properties of brains. So something seems to have happened in that 50 years gap, which I trace in some historical detail with my colleague Joël Abi-Rached in the book Neuro. Despite the fact that there remains what philosophers like to call the explanatory gap between accounting for things at the level of the brain and accounting for things at the level of the mind, despite all the critiques of neuroreductionism, despite all the complaints of philosophers, something seems to be happening. Not mind as brain, but to use the cliche that's becoming pretty common these days, mind is what brain does. The brain has become a knowable molecular mechanism, despite the challenges of its immense complexity and the fact that many of its functions are emergent at level from level. And because of that belief, another belief follows, that it must be possible, in principle, to identify the neurobiological traces of all mental events, to know the mind by knowing the brain, and perhaps to act on the mind by acting on the brain. And that's where I began my investigations of mind-reading technologies, by looking at the beliefs and the hopes that some have that one might be able to read the mind and to act on the mind of others through emerging neurotechnologies. Now, we from the social and the human sciences believe we know a number of things about this area. We believe we know that mental events are not the properties of isolated brains. We believe we know that human brains are shaped for relationality and sociality by evolution, and that our evolved capacities, whatever they are, depend upon the environment in which we're located, the places and spaces and persons within which we're interacting. And we also know that many of the things that we call thinking and memory can't be the property of isolated brains. Thinking depends on language, on writing, on lists. Fabulous paper many years ago by Jack Goody called What's in a List, which showed that the emergence of list making radically transformed the capacities of humans to organize their way through the world. We know that memory depends on the arts of memorizing. Some of us remember Francis Yates' wonderful book, The Art of Memory. Recall is activated by images, by places, by sounds, and so on. Some of us think that cognition itself is distributed around and becoming even more distributed as we become connected up with the internet and with memory devices like our mobile phones and so on. So this little talk is about how you can reconcile what we know, or what we think we know, with the emerging evidence from the neurobiology of brain reading. So I'm going to go through a few examples of what I mean, and I'm going to show you a few little movies, if they work and the sound works, to lighten our evening, and then end up with some questions. But let's just begin with this to start with. Do you know what I'm thinking? Do I know what you're thinking? Do they, or could they, know what we're thinking? Well, about 10 years ago, this article appeared in Nature in 2007, actually. A terrorist pre-crime detector field tested in the United States. This pre-crime detector was an attempt to identify whether individuals were harbouring malintent, malign intentions, and whether or not one could read these malign intentions in some way. And courtesy of the Freedom of Information legislation in the United States, some of the details of this future attribute screening technology, or FAST as it was called, became available, and these are the slides which I put on here from the Department of Homeland Security. Excuse me, I'm behind the screen, so I can't actually see what you're seeing, and I can't point to them with my pointer, so I don't know, can you see my little cursor?
Yes.
You can. Okay, well, you get the picture here. This is probably the clearest one. The idea here, imagine you're in an airport, or imagine you're in an airport and somebody troublesome is also in that airport. You know now when you go to the airport you have to do that kind of thing. Well, instead of doing that kind of thing, the person walks through this little corridor here, and as they walk through this corridor, various attributes of their body are being scanned, and on the basis of those scans, the scans of the face, scans of various physiological measures, pulse, etc., etc., this pre-crime detector attempts to identify whether or not they're harbouring malign thoughts. Now, this got quite a bit of publicity, and at about the same, as you can imagine, especially if you tour the internet, which was even in those days full of conspiracy stories. I'm going to come back to that in a moment. At about the same time, 2007, here was another piece of work that got quite a bit of publicity. Publicised here in The Guardian, the brain scan that can read people's intentions. And this referred to a piece of work by John Dylan Haynes and his colleagues, who had, quotes, developed a powerful technique that allowed them to look deep inside a person's brain and read their intentions before they act. And the report in The Guardian goes on to say this broke controversial new ground in scientists' ability to probe an individual's mind. What they did was they used, quotes, high-resolution brain scans. In fact, they used fMRI technologies to identify patterns of activity before an individual acted, and on that basis read their intentions. Professor Haynes says, using the scanner we could look around the brain for the information and read out something that from the outside there's no way you could possibly tell it's there. It's like shining a torch around looking for writing on the wall. And of course the neuroethicists got pretty concerned about this, and Barbara Sahakian, a neuroscientist and neuroethicist, not long after the film Minority Report had come out, said, do we want to become a Minority Report society where we're preventing crimes that might not happen? From some of these technologies, it's just a matter of time. Okay, a little bit later, 7 years later, this was on the BBC. This is a report about some work from the Jack Gallant's lab. Neuroscience, I built a brain decoder. And well, you can get what they're saying in the image here. The idea is that here, the brain decoder can identify what it is you're looking at. So these are just a little tidbits of the kinds of things I want to talk about today. Now we know that humans, or social neuroscience has taught us, and novelists and filmmakers have told us for years and years and years, that human beings have long had methods to read other people's intentions, to read your eyes, to read your faces, to read your gestures, to read your comportment. That ability to kind of induce internal states into the human is taken for granted in most people's everyday lives. And as I said, it's a capacity that's now theorized in social neuroscience, and actually it's taken advantage of in attempting to diagnose pathologies, the psychopath, the person who's unable to read another's mind, or the autist, the person who's unable to induce mental life into another. But these technologies claim to read thoughts and intentions in the brain itself. And these technologies are being deployed, or at least they have promised to be deployed, in a variety of what one might call ecological niches, in clinical sites where thoughts and intentions can't be expressed in the normal way, a persistent vegetative state. We'll come to that a little bit later on. And as we've already seen, in security practices. So, philosophers agonize over the relations of mind and brain, the attribution of brains of things that properly belong to minds. And many of the researchers here object to the popular designation of what they're doing as mind reading, although they benefit from that publicity. But they're ultimately untroubled by those concerns. Mind is what brain does, and there must therefore be identifiable material traces in the brain, and therefore it must in principle be possible to identify those traces in real time, in the living brain, and make use of them. So the question is, what's going on here, and how should we respond? And I suppose the claim I want to make at the end of this paper is that despite the fact that there's a lot of hype going on around these developments, something is happening. A new materialism of thought itself, maybe even a new topography of the person. Now, I'm not a philosopher, I'm not even a continental philosopher, and I don't claim to understand very much of the work of Gilles Deleuze, although I do read it and enjoy it. But I was struck by a little phrase that Deleuze uses in a couple of his pieces. Le cerveau, c'est l'écran. The brain is the screen. The brain is the screen. So that, I guess, is the motto of this talk. Right, I want to talk about 5 things in the body of the talk itself: deception, intentions, thought identification, simulating the human brain, and beyond the mind-brain problem. And I've got about 40 minutes to do that, so I'd better get on with it. Let's talk about deception, first of all. This is the area that's got most publicity, I guess, and is most problematic. Is it possible to identify deception in the brain? To identify when a person is lying in the brain by reading their brain? There are basically 2 methods that have been developed which claim to do just that. The first, developed in particular in the United States by Larry Farwell, who's not a modest man, I think it's fair to say, if you go to his website, relies on something which is called the P300 wave, which I don't want to go into any technical details, but this is a particular frequency of action in the brain, which is supposedly triggered when an individual sees something or hears something with which they are already familiar. You can see what Dr. Farwell thinks is the use of that. So if you show a terrorist a picture of a training camp, that will trigger the P300 wave. If you show a bomb-making procedure, that will trigger the P300 wave. If you show a person who's committed a criminal act an image of the place where the act was committed, where the murder was committed, that will trigger the P300 wave. That's what Farwell calls brain fingerprinting. And you'll see, if you can be bothered to read all the text, which I'm sure you can't, on the side of the screen here, that he argues that it's an infallible device, it doesn't produce false positives, it doesn't produce false negatives, and he claims that it's being used in the courtroom in the United States to identify whether or not a defendant is lying. Well, I don't think that's the case, and I've not actually seen any of those cases in the United States when it's happened, but it sure has been used in other places. In a very famous case, well, famous in the tiny little pool that I work in, so probably not very famous, a woman called Aditya Sharma was convicted of murdering her husband on the basis of something very like this P300 wave. She actually refused to answer, the husband was poisoned, she refused to answer any questions about this event. She was placed in a brain scanner. The scanner, well, not actually a whole scanner, but just a kind of scanner that could identify the existence of this wave, as you see in the picture in Larry Farwell. It seemed to show that she had foreknowledge. She showed this P300 wave when she was shown the murder weapon and when she was shown the murder scene. And on that basis, she was convicted of murder. That got quite a bit of publicity. What got much less publicity, actually, was the fact that it was overturned on appeal by the Indian Supreme Court on the grounds that an individual should not be compelled to give evidence against themselves. So on that kind of basic civil rights kind of argument. Nonetheless, some versions of this are widely in use in India. And where they're being used is not in the trial itself, because in the trial itself, the judge, like with ordinary fingerprinting, like with the ordinary lie detector test, which is not, which you can't use in most courts, in most jurisdictions, but you can use it outside the court in the investigatory procedure. And even the statement, I'm prepared to take a lie detector test, or the suspect refused to take a lie detector test, plays a great part in investigatory procedures, and those of you who've seen CSI, etc., probably pick that up. Okay, so that's one kind of technology that is being used. Many people think that the P300 wave is a very inaccurate way of identifying foreknowledge, but the belief somehow is that the knowledge is stored in the brain and simply seeing the image will trigger that. The second, the so-called no-lie MRI, again, which has received quite a lot of publicity, relies on a more active process, looking at the active ways in which the brain might work if it's dealing, if it's seeking to deceive those who are asking a question. This works using functional magnetic resonance imaging. I'm not going to go into the detail here. So these are rather crude devices that have not really achieved very much traction within the criminal justice system, partly because of a great deal of concern over what actually is a lie. Is a white lie a lie? Is a falsehood a lie, even if I believe it to be true? Can you extrapolate from what you find in a laboratory to what happens in the courtroom, in real life? In real life, where the very fact of being accused of a crime generates quite unknown patterns of brain activity, and when those who are genuinely guilty are probably likely to have all sorts of methods to disguise their deception. Nonetheless, these kinds of technologies are gaining a little bit of traction, not in the courtroom itself, but outside the courtroom, where the rules that govern admissibility of evidence simply don't apply. And like many other of the pieces of research which I'm going to talk about today, this work on lie detection receives considerable financial support from the US Department of Homeland Security, which was considerably increased after 9/11, and there's some great work on this by Melissa Littlefield, which I've drawn upon here. Okay, so that's deception. What about intentions? So I've already shown you the fast technologies to read the mind in the body, but in fact that's a little bit of a diversion, because these fast technologies, the ones I showed you walking through the airport and so on, they just work on the external physiology of the body. Are you showing that you're tense by your eye blinks, or by the rigidity of your mouth or your cheek? Are you sweating a lot, etc., etc., etc. So they really just look at the surface of the body to read the intentions. This one, the one by John Dylan Haynes, looks as if it's getting more to the point of actually reading the brain itself. And I already showed you this slide and what John Dylan Haynes said. Using the scanner, we can look around the brain for information and read it out, that from the outside, there's no way that you could tell. So what was this study that Haynes and his colleagues did, which was like looking for writing on the wall, looking into the brain? Are we really in danger of becoming a minority report society? So here's where, although I don't wish to be critical, one might want to keep one's critical antenna alert. This study that got that publicity was a study of 8 volunteers, and the volunteers who were going into an fMRI, functional magnetic resonance imaging machine, were given a task, and their task was whether to add or subtract 2 numbers. So they were given that task, they had to decide whether to add or subtract 2 numbers, say, keep it to themselves, and then they were scanned with a fMRI, which focused on the medial prefrontal cortex, and in 2/3 of cases, when the experimenters looked at the brain scan, they were able to predict whether or not the subject would add or subtract on the basis of the brain region which was activated. So in 2/3 of cases, what's 2/3 out of 8? Oh, that can't be right, actually. Even my statistics show that that can't be right, but you get the point. In so the slight majority of these cases, the researchers looking at the scanner could decide, without knowing whether the person did actually add or subtract, by just looking at the regions of the brain that were activated, whether the individual could add, was going to add or subtract. Now this seems a very, very long way from what one might consider intentions in the real world. My intention to have a glass of red wine or a glass of white wine, your intention to check your Twitter feed because you're completely fed up with this talk, etc., etc., etc. Nonetheless, you see a sneaking edge here of something that is significant, which is that intentions before action have legible traces in the brain. Now, there are a host of scientific and technical questions around this type of research, not least the basic thesis of localization, that this region is involved when you're thinking of adding, that region is involved in the thinking of subtracting, not least that this is done in an incredibly artificial laboratory environment, etc., etc., etc. But nonetheless, the hypothesis is emerging that mental events are visible in the tissues of the brain, and that it might be possible to develop an objective technology for reading the mind. So let's see if we get any further with this objective technology for reading the mind by reading the brain. Let's look at what's called thought identification. Now, every student of psychology knows the work of Carl Lashley. What Lashley tried to do was to identify the engram, the place in the brain where a memory was stored. And what he did was he trained rats to run mazes, and then he chopped out bits of the rat's brain. He trained lots of rats to run mazes, and he chopped out lots of bits of the rat's brain. But he found it, however many bits of the rat's brain he chopped, he couldn't abolish the habit in the rat of running the maze. Somehow he was, wherever that memory of how to run the maze was stored, it did not seem to be stored in a physical location. Now, that led to many researchers thinking, okay, there are no simple physical locations for storing memory. Wherever memory is, it's not in one place. And because it's not in one place, it's highly distributed, it will be pretty difficult to reactivate it or to read it. So on the other side of the screen, from the picture of Carl Lashley, you'll see the cover of a National Geographical magazine. And those of you who are familiar with popular culture might be intrigued to see the montage of pictures that are below that, which come from that issue of the National Geographical magazine. And those of you who are very familiar with popular culture might recognize that those are all pictures of a famous performer called Jennifer Aniston. We'll come back to why Jennifer Aniston in a moment. Of course, there have been attempts to identify places in the brain where a memory is stored. And a lot of those, the later attempts, start from the work of Wilder Penfield. Penfield, who was working in Canada, was working with people who had intractable epilepsy. And he and many others thought at that time that if someone had intractable epilepsy, one of the ways of, really, really bad epilepsy that you couldn't control in any other way, one of the ways of dealing with that epilepsy, mitigating that epilepsy, was to find a small focal point in the brain where the epileptic convulsions began, the foci of that epileptic seizure, and to ablate them, to remove them. Penfield and others developed this technology where they'd open up the skull, and I'm sure most of you know here that inside the skull the brain has no sensory feelings, it's got no nerve endings, so you can mess around in there and the person is not going to feel any pain once you've anaesthetised the top of the skull. You'd open up the skull and then you'd try to identify this focal point of the epileptic seizure in order to ablate it. And what Wilder, Penfield and his colleagues tried to do was to identify which bits of the brain they shouldn't damage in any way. And in order to do that, they stimulated different areas of the cortex. And on the basis of stimulating this area of the cortex, Penfield created these lovely maps that I'm sure many of you are familiar with, which show which areas of the cortex are related to which area, to sensations in which area of the body, because you stimulate one of them and you get a sensation in your foot, another you get a sensation in your cheek, another you get a sensation in your hand, and so on and so forth. From our point of view, I mean, that's all terrific. Very fond of his work, but from our point of view, the interesting thing is this, that when Penfield stimulated some bits of the cortex, the subject, who was awake at the time, of course, with the skull open, who was awake at the time, recalled a memory, a very distinct memory. I'm sitting in my mother's kitchen on a blue stool, and there's a white refrigerator, and my mother is cooking cakes, and I can smell the smell of the cakes that she is cooking. Or I can hear the sound of the music that was playing. In a small percentage of patients, some very specific visual or tactile or auditory memories seem to be produced simply by a small stimulation of that area of the cortex. Now, Penfield had his own views as to what was going on there. Many people cast doubts on whether or not these were real memories or fabricated memories, etc., etc., etc. So, why Jennifer Aniston?
Those biomarkers and our capacity to measure them leads us naturally to Jennifer Aniston. If we could have the next...
this is Christoph Koch,
video.
by
So
the way.
we have very rarely the occasion to measure the response of the brain at the level of individual nerve cells, because for obvious reasons you can't access the nerve cells in a human brain. We can only do it by and large in experimental animals. But sometimes, particularly during neurosurgery, you can actually listen to individual neurons. Now inside the brain it's silent, right? There's no sound, but if you put in a microelectrode and you can listen to the individual nerve cells chat to each other, you can hear, in fact, I think we have a recording, they have the sort of staccato sound. If you take the electrical signal and amplify it and put it on a sound speaker, you can actually hear them talk to each other. Each one is a little, each tick is a little action potential, it's a little pulse. So this is actually a recording from a surgical measurement where the neurosurgeon put a microelectrode into the brain of a patient, and this nerve cell responded very selectively only to pictures of Jennifer Aniston.
I think it's fair to say Team Angelina.
It is true. It is true. It was because why Jennifer Aniston? It's not that we're born with Jennifer Aniston neurons, at least hopefully. But we're born with a disposition to learn things So, you know, your mother, your parents, the president, famous actors and actresses. So here, by mere chance, we have to come upon a neuron that selectively encoded the presence of Jennifer Aniston. And sometimes you find cells that even respond to the name Jennifer Aniston or to the name of the famous person. It could be a sister, it could be your friend, could be your mom, could be a famous actress.
So, here seems to be an engram of Jennifer Aniston that will respond to the name, the film, the picture, somehow encoded in that little bit of brain is your memory of Jennifer Aniston. Doesn't seem to require a whole lot of other stuff that us social scientists and human scientists know the supports of Jennifer Aniston. We don't have to be going to the cinema, or we don't have to be thinking about movies, or we don't have to be thinking about whatever the perfume is that she advertised or anything. Just hit that cell, Jennifer Aniston. And by extension, Jennifer Aniston, your mother, your father, your dog, your car, and perhaps by extension, every single thing. Remember, we're talking 10 to the 10th neurons here, 10 to the 11th synapses, millions and billions of neurons. Perhaps each of those encodes a specific memory. Perhaps that's what memory is. Perhaps memory is not a mental thing. Perhaps it's a neural thing. So, this is what's called thought identification. And this, I'm taking this from a program on American TV, is the work of two researchers at Carnegie Mellon, Marcel Just and Tom Mitchell, who did an experiment where they showed individuals objects. They asked them to think about objects. 5 of them were tools, things like screwdrivers and hammers, and 5 of them were dwellings, like igloos and castles. And they put these individuals into an fMRI scanner, and they used various algorithms in order to process the data that came out. And this is what they said. The computer found the place in the brain where that person was thinking screwdriver. Screwdriver isn't one place in the brain, so like memory of a maze is not in one place of the brain. Screwdriver is in many places in the brain. When you think of a screwdriver, you think about how you hold it, how you twist it, what it looks like, what you use it for, just Marcel just explained. When we think screwdriver or igloo, for example, just says neurons start firing at various levels of intensity in different areas throughout the brain. And we found that we could identify which object they were thinking about from the brain activation patterns. Okay, so the important thing about this is not that when you think about screwdriver or igloo, lots of bits of the brain are firing. We could take that for granted, couldn't we, these days? But what's interesting here is that they say by placing those patterns of brain activation into a computer, the computer can read out what they're thinking. And indeed, in this American TV program, the presenter is stuck into an fMRI machine and asked to think about certain things, and they begin to identify absolutely what it is that she is thinking about. And then there's a lot of discussion about, does your boss know what you're thinking? Is your husband going to know what you're thinking? Your wife going to know what you're thinking? Etc., etc., etc. So something interesting is happening here. Not just the fact that the brain is activated, which we know, but that you can read those brain activations. This is work by Jack Gallant's lab and Shinji Nishimoto. And this is another example of brain reading or thought identification. In this case, they showed individuals pictures. The brain was activated when the individual saw the picture. They used various technologies in order to pick up the patterns of brain activation. They analyzed them using algorithms, computer-based algorithms, and on the basis of those algorithms, they could reconstruct the picture that they were seeing or the picture that they were thinking of. Okay. So again here, not just Jennifer Aniston, not just a sound, and a whole organization of visual space appears as if it can be read out of the brain itself without the intervention of speech, without the intervention of mental events, without the intervention of any interpretation apart from an analysis by algorithm. Here's another example of how this kind of work happens. These are the headlines that reported that work. Mind-boggling. Science creates a computer that can decode your thoughts and put them into words. Science decodes internal voices, and so on and so forth. Well, it wasn't quite that simple as you can imagine. What happened here was that people who are undergoing brain surgery had a cortical implant placed on the cortex with 256 electrodes in that cortical implant. And as they were connected up with that cortical implant, They listened to people saying certain words, nouns, verbs, and names of individuals, and the computer program analysed the activity from the electrodes and tried to reproduce the words that they were hearing. It didn't do very well. Only 47 of the words were reproduced. Humans couldn't understand which words they were, but nonetheless, these reconstructed words from the patterns of brain activity themselves seem to indicate that you could indeed read the mind by reading the brain. Robert Knight, who was the person who oversaw that research, said this is huge for patients who have damage to their speech mechanisms because of a stroke or Lou Gehrig's disease, motor neuron disease, and can't speak. And indeed, this is one of a number of these technologies that are being used in order to access the thoughts of those people who are unable to express their intentions in what's become the normal way. This work by Adrian Owen and his colleagues also attracted quite a lot of attention. This was another brain reading technology in which individuals a small number of the individuals that they looked at in persistent vegetative states were able to communicate by patterns of brain activity. To be very simple about it, questions were asked and the individual was said, if the answer to that question is yes, imagine you're playing tennis. If the answer to that question is no, imagine you're walking through your house. Different patterns of brain activity are generated in each of those two examples, and on the basis of that, the individual can say yes or no. That's rather simple, although did generate a rather intriguing and difficult set of ethical questions about how one should treat then people who were in persistent vegetative states. And if only some of them were able to express their intentions or to say whether they were in pain or not in pain, as this individual down here did, what did that mean for the others who were unable to express their intentions in that way? Might they also be locked in their thinking, alive, but unable to communicate? In fact, the Jack Gallant's lab has done a great deal of further work on these attempts to reconstruct thought patterns by brain reading using advanced computational equipment. And I won't go, for reasons of time, I won't go into the details of what they've done there, but if you go to Jacques Gallant's lab, you'll see some ways in which they map out semantic space across the brain, and they map out these things, and you can see those in those pictures there. So, many object to the term mind reading and prefer thought identification. The technologies are currently in their infancy, but they seem to demonstrate the possibility, as I said, of identifying and using mental events by accessing their physical traces in the brain. These are classical dual-use technologies. They can be used for clinical purposes, but they can also be used for security purposes. And they can be used not just for reading out from the brain, but potentially also for reading into the brain, potentially managing the person by modulating the brain. To manage the person by modulating their brain, surely that's a bit of a sci-fi fantasy. But you can imagine the uses of it in certain circumstances. You can imagine, for instance, an individual who has paedophilic tendencies. You can imagine a brain reading technology that will identify when those attractions are beginning to be generated. And you can imagine, can you, a brain reading technology that would also be a brain writing technology that would seek to ablate or restrict or mitigate those regions of brain activity. So what's happening to our sense of ourselves here?
With a
astonishing dexterity, a monkey reaches out to grab and turn a handle with a robotic arm controlled not by its hands, but directly by its brain. With the power of thought, it can alter the speed and direction of the arm, twisting the joints to home in on its target. It shows no signs of distress from the wires leading from electrodes in its brain to a computer. The reward for each turn of the handle, a drink of water.
So what's happening there is based on the idea that when the monkey, in this case, thinks of moving its arm, you can, a proportion of the motor cortex, proportion of the cells in the motor cortex are activated. And if you have an implant into that area of the brain, that can identify when those are activated, and by computer technology it can move a prosthetic arm. So the monkey is thinking of moving its arm, and the arm moves.
In this paper, 2 people with tetraplegia, that is 2 people who are unable to move their arms or their legs in any functionally useful way, were able to control a prosthetic or a robotic arm simply by thinking about the movement of their own paralyzed hand. And they did that using the investigational brain-gate neural interface system. So they thought about using their own arm and hand as though they were reaching out themselves with their own limb, and the robotic arm moved much the way their own arm would have moved. One of the long-standing questions, not only in neuroscience, but in neurorehabilitation, is whether the cells in the motor cortex and other parts of the brain, whether they continue to function the same way years after that original injury.
It is possible for people to use their thoughts to control devices, either a computer or a robotic arm. The way that happens is that we implant a tiny sensor, just about the size of a baby aspirin, just into the surface of the brain, and that sensor pick up the electrical impulses from a bunch of neurons. And each of those little neurons are like radio broadcast towers putting out impulses. And when they get to the outside, a computer translator converts the pattern of pulses into something that is a command.
One of our participants was able to do something that, when all of us saw it for the first time, gave us all pause. She reached out with the robotic arm, she thought about the use of her own hand, she picked up that thermos of coffee, brought it close to her, tilted it towards herself, and sipped the coffee from a straw. And that was the first time in nearly 15 years that she had picked up anything and been able to drink from it solely of her own volition.
I said these are dual-use technologies. I mean, no one can fail to be moved by their power for people who've lost the capacity to move their limbs. But it's also worth noting that a lot of the research in neuroprosthetics is actually the work that's done in the United States is funded by DARPA, the Defense and Allied Research Projects Agency, DARPA. Some of you may have seen the kickoff of the previous World Cup, I think it was, in Rio. The first ball that was kicked in that was kicked by a man who was tetraplegic, and he was in an exoskeleton which he was moving by the power of his thought to kick the ball. That work was done by Miguel Nikolas' lab, and Miguel Nikolas' lab is funded very extensively by DARPA. And this is the kind of work that you'll see on the screen there that DARPA is trying to use these kinds of technologies for reading brains, and indeed for implanting signals into the brain for all sorts of reasons that you can well imagine. DARPA makes no secret of its great investment in the development of these neuroprosthetics. Obviously, they have a lot of military personnel who come back from the conflict and have spinal cord injuries, are unable to move their limbs. And indeed, DARPA's doing a great deal of this very advanced research, reading out from the brain and trying to develop technologies to read back into the brain. Now, those of us of a historical bent will immediately think of the work of José Delgado. José Delgado, a Spanish neuroscientist who was funded by the American military in the 1950s and the 1960s. Delgado started his work because he was horrified by what he thought were the crude assaults on the brain of the frontal lobotomies, which he was seeing all around him at that time. And he thought there must be more sophisticated and subtle ways of affecting the brains of individuals. And he developed his technology called the stimoceiver. You can see the monkey here with a stimoceiver in its brain. It is a cortical implant that can both read out signals from the brain and read in signals from the brain. That's Delgado there. And this is the book that he wrote, or rather published, in 1969, which was called Physical Control of the Mind, and perhaps unwisely was subtitled Towards a Psycho-Civilized Society. So think the paedophile with the brain implant that can read in, can read out, and read in. Does that ever work? Somebody will have seen this before. It's in French.
Prenez par exemple un taureau espagnol. C'est méchant le taureau espagnol, non? Eh bien, erreur. Cette année, les taureaux espagnols, eux aussi, promettent d'être beaux. Que dis-je beaux? 10 000 presque. Il aura suffi pour cela d'un petit émetteur à transistor, celui que tient cet homme, l'un des assistants espagnols du professeur Delgado de New York. Sur la tête du taureau, on a monté un récepteur dont les fines électrodes s'enfoncent, sans douleur, paraît-il, dans le cerveau. Désormais, il suffira à l'assistant d'envoyer un signal d'onde de son émetteur pour que le taureau atteint dans ses centres nerveux devienne craintif comme un moineau. Essayons. Voilà notre taureau à son état normal, je veux dire comme étaient encore les taureaux en 64. Il voit la cape, il fonce, rien n'est changé, bon.
So the bull hasn't changed at all. There's the bull in the corridor.
Maintenant, envoyons le signal. Taureau, 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 taureau. Pas de doute, c'est bien le triomphe de la technique. On nous avait déjà dit que le transistor changerait notre vie, mais à ce point, notez que pour l'instant, on n'a essayé encore que sur des taureaux. Mais la promesse est là. Maintenant, soyons sérieux. Voici une vraie carte de vœux sincère. Elle vient d'Égypte, où des hommes qui n'en sont pas encore à domestiquer les taureaux avec des transistors ont rapporté cette année sur la nature une victoire plus utile et plus grandiose.
You get the point. Now, I'm not saying that DARPA and José Delgado are the same, but I'm saying you're beginning to see technologies that can read out from the brain and read in from the brain, read into the brain. Now, I was going to talk a little bit about the Human Brain Project here, but I see my time is running out, so I was going to just say a little bit about these attempts to actually simulate brains in supercomputers. These are some of the old versions of that in the 1950s and in the 1960s. Well, the Human Brain Project has changed a lot since its earliest inception, but at least in its earliest inception, in the work of Henry Markram, one of the key aims of the Human Brain Project was indeed to simulate the human brain, neuron by neuron, in a supercomputer, to create computer models of every type of neuron in the brain, to place those neurons into something like cortical columns, the columnar structure of the cortex, in the right combinations that one might find from experimental data, to see how those computer simulated neurons connected up with one another, and to see the way in which they generated higher level activities within the brain. And the aim of this simulation of the human brain in a supercomputer was both to understand the materiality of the brain and then also to begin to understand what happened in neuropathologies. Now, the only point of pointing to those here, and I don't have time to go into it, is to say that the central assumption or the premise there is that higher mental functions are emergent from the physical properties of individual neurons. And indeed, these are the kinds of arguments that were made around those computer modeling brain technologies, trying to generate the capacities of the human brain and then its higher cognitive capacities from the material properties of the neurons themselves. Science fiction or science fact? Well, for many, at least the hint of something that is moving from science fiction to science fact. Now, I don't want to say that Christoph Koch, who you saw earlier on in the slide, that of the Jennifer Aniston neuron, is the most prescient of analysts of these things. But Koch argues, and you'll see that there in the yellow box, that he's got no doubt that these images of machines generating mental events through simulating brains within their computational capacities are moving from science fiction to science fact, and that they will soon be able to pass the Turing test, which is to say that you will be unable to tell whether something generated by one of these machines is being generated by a high-level neuromorphic computer or generated by a human brain. Let me move rapidly to my conclusion, because the aim is to get some discussion. So what's happening here? I started this investigation by just looking at the new technologies that were emerging, and I think there's a lot to be said about those new technologies and what they do and what they don't do, and the capacities that they have to read in and read out, and what might be the implications of that, etc., etc., etc. But as I came to the end of this investigation, it seemed to me that something else was beginning to happen. A new way of thinking about human beings in terms of their neurobiological constitution. That many of those things that we had habitually attributed to mind, to a mental state, to something that was emergent from the neurons, but not identical with them, was beginning to be remapped onto the brain itself. The enormous number of circuits between the 10 to the 11th nerve cells, the 10 to the 15th connections between them, which have been shaped by development, which were constantly changing and morphing in response to internal and external inputs, that these not only generated the possibility of mental states, but in fact, perhaps they were those mental states. Perhaps those things that we call mental states are unconscious mental states, unconscious, that we have classically attributed to a kind of Freudian notion of a mental sphere which is impermeable to consciousness, are actually not in some mental sphere, but are in the neurobiology itself. That there's a kind of materialism here, that we're beginning to see the emergence of this sense through technology, that mind is what brain does. Whatever the concerns of the philosophers, that mind is what brain does. Now we know what the response of many philosophers is. Only persons in relations with language, with culture, with meaning, etc., etc., can think, can know, etc., etc. The brain no more knows than a dictionary knows. But must we always suppose a mental realm that's different in substance or extension from the brain? These objections seem to me to have been outflanked, not resolved by philosophy, but somehow outflanked by technology itself. Now, for those of us who grew up as theoretical anti-humanists, concerned that we had given far too much power to the idea of the ego, the idea of consciousness, don't actually find anything tremendously new here. Nietzsche, it's a falsification of the facts to say the subject I is the condition of the predicate think. It thinks, but but that this it is precisely that famous old I is, to put it mildly, only an assumption. It's wrong to say I think. One ought to say I am thought. And Freud himself seemed to argue that the radical nature of the work that he was doing was a wounding blow to human megalomania. But perhaps this is an even more wounding blow to human megalomania, to think that it is the brain itself that thinks. So how should we respond? Certainly, I think we need to analyse the truth claims of some of these technologies and those who report them. We need to cut our way through the hype. But it seems to me also that one ought at least to contemplate the idea that something more significant is happening here, that we're beginning to see the emergence of a new materialism of the brain, and that is something that those of us who are social and human scientists, who've constantly stressed the importance of language, of culture, of meaning, of history, of social interaction, of sociality in all its senses, need to begin to come to terms with, in thinking about what it might actually mean for the brain to be the screen. C'est l'écran. What does that mean? Well, that's where I ended up after my investigations, and that's where I'm going to stop.